Greetings to all. My name is Narsingh Rao. I work in Oak Ridge National Laboratory as a research software engineer. The topic of my presentation is about the hierarchical task scheduler for the heterogeneous computing. Okay, let's see some trends of the heterogeneous system. So the current mobile platforms are coming with the heterogeneous computing units. They are not just equipped with the CPUs and GPUs, they are also equipped with the accelerators for the camera ISP and the hexagon DSP and also LTE and 5G modems. This trend will continue more and more with the more heterogeneous accelerators in the platform. And we can see some similar trends even in the supercomputing platforms, where the computing units are not only CPU and GPUs, and now they are being equipped with the FPGA accelerators. And we can see more and more domain-specific accelerators in the supercomputing nodes. And it actually aligns with the DOE roadmap to the exascale computer systems, so where the future systems will be equipped with the domain-specific accelerators, which are more and more heterogeneous in nature. So if I see challenges of having these heterogeneous systems, so with the heterogeneous accelerators, the biggest challenge is having these heterogeneous accelerators integration in the SoC. And of course, the biggest challenge is scalability, how we can have these tens to hundreds of these heterogeneous accelerators in the platform. Okay, and programming is another big challenge where how we can actually access these heterogeneous accelerators and how we can do the data transfers to the accelerators and get the maximum computing out of it. And in programming, there is another big challenge is interfacing these accelerators with the application. So these accelerators are being designed with the specific APIs, and the application has to call these APIs for its functionality, and there should be some specific interface for this one. And data transfer and bandwidth is also another big challenge. So when we have these tens to hundreds of these accelerators, so it will pose a very important challenge of how they share this bandwidth on the shared interconnects and also shared memories. And on top of this, the biggest challenge for the applications is how these applications can exploit the optimizer mix span. So exploring these heterogeneous computing features, where it has a lot many possibilities to map its application task on these heterogeneous systems. Okay, so another big motivation for this heterogeneous systems is because of this open source hardware movement by the RISC-V community. So where there are many vendors are coming up with the RISC-V based boards, and they are coming up with the RISC-V based accelerators. Okay, so about this paper, so we are actually proposing a task scheduling for this heterogeneous accelerator system, which balances the application performance and maintains the application programmability for these accelerators. And it actually explores the varying data communication time between tasks and map the task to these accelerators, and also explores the varying computation times across these different variants of these accelerators, even though they are for the same computation. Okay, so in summary, so I say that this proposal is about the platform that we propose. We call it as a Ranger platform, which is having a hardware-assisted task scheduling framework. And it is based on RISC-V cores, where the accelerators are associated with a tiny RISC-V processors. And we propose a hierarchical task scheduler for this Ranger platform, where at the local level, the fine-grained tasks will be performing and calling these accelerators, which are very accelerator-specific tasks. And at the global level, we are having very coarse-grained task specification for the programming portability purpose. And we actually model this platform in the JUMP5 simulator. Okay, so let's see some state of the art. So, okay, so when we have the accelerators, the accelerator tasks are usually streaming in nature. because of the its limited SPM constraints for its input and output buffers. Okay, so there are okay, in the case of task scheduling, there is a lot of literature in the state of the art. So for the because of these accelerators are very heterogeneous in nature, so the list scheduling based methods can be applied. The earliest heterogeneous finish time scheduler in 2002 is proposed based on the priority given to the finish time of the task. So, but it doesn't have the capability to look its impact on the future tasks. So, which is actually proposed in 2010 by look ahead method. So, but it is very complex method, order of n power 4, where n is number of tasks. And its complexity is reduced in the PEFT method in 2013, but its complexity is order of n squared. So, but overall, the complexity of this scheduling algorithm depends mainly on the number of tasks and the task metadata, like the computation cost metrics, like how much time it will be taking the task on each processor, and then how much time the data transfer from one task to other task it requires. And then it also depends on the it's a task dependency, like the task graph. If you have a complex task graph, it will impact on its scheduling time. So there is some hardware scheduler also proposed using rocket ship, which is actually using the basic scheduling algorithms for the coarse grained task. So in the state of the art, what is lacking is that, okay, all these approaches are considered as centralized schedulers, but we can't actually use them for this accelerated task, which are streaming in nature. If we consider all those stream tasks as a fine-grained task, then it is too many, and it will bloat up the complexity. And because of this accelerator tasks are streaming tasks, so accelerator controllers also needs to be more generic, and they should be more scalable. That is also one more challenge for this platform. Okay, so we propose a hierarchical task scheduler, where the coarse-grained task scheduler take care of programmability, and which considers only coarse-grained task graph. And the fine-grained task scheduler, it actually for the accelerator stream task. Okay. Let's say some basic notions in this state of the art. Okay, the task is an atomic unit of the computation. So, and it also associated with the data transfers for its inputs and outputs. So it can be portioned with the subtask, particularly for this accelerated task. Each task is considered as a fine-grained subtask, set of fine-grained subtasks. And the accelerator will actually can take only some small chunk of input and can do the computation and can send back its output back to the memory. So this actually gives us a more scheduling opportunity. But when we consider all these accelerator streaming tasks as a subtask, then it will actually increases the scheduling complexity. Okay. And one big advantage with the streaming task streaming task of the accelerators is that because they can actually go, the data transfers of this streaming task can overlap with the computation, so that they can go hand in hand with the data transfers and computation. Okay, so here an example task graph, and the corresponding cost computation matrix is given for the 3 different processes, where the edge shows the data transfer time from one task to other task. Okay, so let's see the baseline platform, which is a state-of-the-art heterogeneous accelerator platform, where we can where we have the applications. We uses some runtime framework to give the task to the centralized heterogeneous scheduler. Okay, and the task will be dispatched to these accelerators to this. Okay, it can have several accelerators, and each accelerator can be associated with its DMAs. Okay, so in this case, we can clearly see that the complexity of this centralized scheduler depends on the number of tasks it has. And so if it deals with the fine-grained task, then it will be spinning, its complexity will bloat up actually. Okay, so, and there another big challenge is how we control these accelerators and DMAs. So it can be controlled either with the host application itself in the fine-grained task. But as I said, it will lead to a huge number of fine-grained tasks, or it can be actually configured through at the very coarse grain level, but it actually considers that, assumes that the accelerator will be having enough memory to hold all its inputs and outputs. That means it requires very bigger scratch pad memory. Okay, so that is one big disadvantage with this baseline platform. Okay, so we propose a Ranger platform with a heterogeneous accelerator. So in our platform, we consider that the accelerator is associated with small tiny RISC-V process. Okay, and we actually model this Ranger platform in the jump file, and it actually reuses most of these components of the RISC-V, and then the shared bus and memories and memories, and we develop the components like accelerators and the DMAs and FIFOs, task FIFOs. Okay. In the Ranger platform, so the RISC-V based device, it actually take care of the controlling the stream task, and also it actually configures this DMAs and accelerators. And it is, because it's a RISC-V is a programmable, so we can actually make it more generic for the accelerators. Okay, and we consider the PFT as centralized scheduling policy for the coarse grain task scheduler. Okay, and the interface between the RISC-V and the accelerators or DMA is memory mapped IO. So, yeah. Okay, so let's see how this hierarchical task scheduler flow will work. So we are at the very at a very high level. So the first level scheduler will take this task graph from the application, and then based on this computation metrics, computation cost metrics. So it will actually map the task to the devices with the accelerators, and the task the RISC-V device the RISC-V processor on the device will actually have the accelerator specific command scheduler. So each task is having the commands like DMA input and kernel and output. So it will actually map these commands in a stream fashion, so to this DMAs and the accelerators. And as these are stream tasks, we can actually overlap this DMA input and output, so in a pipeline. So this is one steady state, and for each of these DMAs and accelerators, so for each subtask, so there will be some configuration time and some initialization time will be there. Okay, so one big advantage from this hierarchical task scheduler is that the fine-grained scheduler is programmable and accelerator specific, and it actually can balances the data transfers of the input and output, and can completely overlap with the computation, so that all these data transfers can be hidden. So if you can find the kernel with a computation with the right data reuse, so that can be programmable to run on the device, the RISC-V device. That is one big advantage. Okay, so let's see some experimental setups. So as I said, we actually model this platform in jump file. So we use the DNNs to benchmark, like a popular DNNs, Inception V3, ResNet, and UNet, and VGG60. So we use TensorFlow models of these networks, and then converted into the task graphs of our runtime framework. And then the accelerators that we use for regular experiments is 3 convolution, batch management, and dense, but we actually use different configurations, MAC units of the different variants of these accelerators, so that we actually got nearly 15 accelerators with this variant configurations with the different scratch pad memory sizes. Okay, so with these combinations, we actually derived to the different designs 1 to 10. So where we actually varied only the convolution accelerators. In design A to H, where we actually varied both convolution accelerators and batch convolution dense accelerators. Okay. Okay, so in one experiment evaluation, we actually monitored the mix band. So where you can also see the we compared with the baseline architecture. In the baseline architecture, we consider the fine-grained tasks of the streaming task of the accelerator. So that actually, if I have 189 tasks in the ranger for the inception v3, so when we actually have the very fine-grained task in the baseline, so it is 20,000. So it is a 108 per x increase. So this actually leads to the lot of synchronization and control overhead. So this actually resulted in the very big gain in the ranger, the nearly some 12.7x speed up in the make span for the four different networks for the different designs. Okay, so we also did some scalability experiment, like we actually fix this number of instances of each applications to the 10 in this case. So we actually increase number of accelerators in this experiment so that we want to see how much it is scalable. And we actually see the saturation point at the design choice of 3. So where it requires 35 accelerators, and the speed up over the base case is it is not increasing, not more than 2x. Approximately 2x, but the baseline is actually stop scalability at 1x itself in the design choice 1 itself. So ranger is scalable, but it is limited. But it is also because of lack of not having enough number of tasks when you have the more number of accelerators. Now we did one more experiment to actually increase number of application instances from 4 to 100. So there we can see that ranger is very good scalable when we actually increase its number of instances of each application to 100. Okay, so we also want to check, okay, so now if we have the baseline with the enough memory, so then it will be having only the coarse grained scheduler. So then it will be having, it can do decent job. So we want to compare with that, but this kind of design is very hypothetical. We call it as a reference design, which is not possible to actually implement in hardware because of it requires huge scratchpad memory. So in this case, we see that the difference between the reference and ranger for the inception v3 and ResNet is very minimal, and the ranger is doing much better in the make span. But we can actually see that in the case of VCC and unit, so it requires actually huge data transfers across the layers. So there the reference is doing better job, but as I said, this is very hypothetical architecture, so it is not possible to realize in reality. Okay, so the conclusion, yeah, we presented this ranger framework, and which is an architecture designed for the hierarchical task scheduling, and it is actually shown with the jump 5 modeling. So in the proposed hierarchical task scheduling, so it requires a coarse grained task graph dependency and very fine grained accelerator specific scheduling at lower level. Okay, so we use the RISC-V course in the ranger platform for the programmability and also for scalability, and our platform has achieved some 12.7x performance gain in terms of make span, and the area overhead is just 2.7%, little higher compared to baseline, because when compared to baseline, so ranger is having the tiny RISC-V course, which is adding very little overhead on the area. The future work, we see that, okay, yes, we have this platform, that's very good, but the problem is how to determine what is the best set of accelerators for this domain-specific application, which is a very good design space exploration problem. And the another possibility that we see is how can we actually make this hierarchical task scheduler with the hardware task scheduling implementation. So that is another future work that we see. Yeah. Thank you very much. If you have any questions, please mail me, and please refer to my paper for more details. Thank you.